Okay, so 9:02, let's start it. It's my pleasure to introduce Mr. Tim Lenze. He has been working at Deltares, which is an independent research institute based in Delft, Netherlands. Since 2018, he is working as coastal researcher and engineer, advising and researching topics regarding the modeling compound flooding due to extreme event, including tropical cyclone. Since then, he has been involved in several national and international projects and has gained broad experience in application of coastal modeling software such as DAS3D, DAS3FM, SWAN, Sphinx, XBeach. Within these, tropical cyclones, storm surge, wave propagation, compound flooding, and coastal hazard topics, he is involved in model validation and development of Sphinx, depth dashboard, HydroMT, and TCYs. For Sphinx, it is acronym Superfast Inundation Cost. He is acting as the product owner within the Deltares hydrodynamic product line, guiding the development of model. As of September 2022, he also joined the Institute for Environmental Studies of the Vrije University Amsterdam as part-time PhD candidate, working on improving large-scale coastal flooding risk assessment by including wave-driven components dynamically. So please welcome Tim today. So whenever you're ready, you can start.
All right, thank you very much for this introduction and allowing me the opportunity to speak to you all. I'm coming from the Netherlands, from The Hague, for you today, and I will be sorry?
Could you please unmute?
Okay, and I will be talking about how we are developing new fast tools for assessing coastal compound flood hazards. Most of it will be about Sphinx, but also some other new tools. And as I said, I'm a researcher at Deltares, where I'm the product owner, product manager of the Sphinx model, however you want to call it. I'm indeed also doing a part-time PhD at the Vrije Universiteit in Amsterdam. I'll go sharing my screen, which you should be able to see now.
Yes.
Perfect. So the motivation, sort of the general storyline of this presentation, is that we have these new fast tools for assessing coastal compound flood hazards, and that we're developing at Deltares, but also with other partners. And the idea is that we want to assess coastal hazards better or more quickly or for larger scales, and ideally all that together. And this now leads to new opportunities for flood risk assessment and early warning systems. And I will go through a couple of highlights through my talk and talk a bit about different types of models and try to show as many pictures and animations as possible. And a lot of this presentation is also a combination of what my work of what my colleagues have done. So Maarten van Ormond, Kees van Nederhof, that are part of Deltares USA, and then some others like that van Dongeren, Roel de Goede, Robert Mokhol, and Roel Vink. It was already said a little bit. So Deltares is an independent knowledge institute based in Delft, the Netherlands, and we've worked on a lot of innovative solutions in the field of water and subsurface for many, many years. And I'm there part of the coastal hazards team. We're mostly focused on hydrodynamic and morphological processes regarding coastal flooding and erosion, mostly focusing on wave-driven events, but nowadays also a bit broader on coastal flooding. We do this for a range of coastal environments, so sandy coast, but also gravel and coral, vegetated and built environments. And our group developed a lot of software. So XBeach comes from our group, TCY, Tilted Board, and so things. So I sort of schedule my talk in general, talk a little bit about compound flooding, why we should not forget about waves, the importance of including probabilistic estimates, and then how we are using 3 new models for that: hurry wave, snap wave, and Sphinx. And we'll talk a bit more in detail about Sphinx and recent developments. I added some slides in general talking about like working open source and open access when developing these models. And then if I have time, I will show 2 other tools briefly that go more about the output of what you can do with the model. The compound flooding in general. So I start with this figure in Charleston, in South Carolina, where you can have an estuarine setting with different rivers, including the Cooper River, which is the larger one. You have some barrier islands. And you can see from the parts that are blue and red during a historical storm, it is a very vulnerable environment. It's quite low lying, and you can imagine that if, for instance, during a hurricane, storm surge and tides push up the water level offshore, but at the same time a lot of water comes from the river downstream, and that at the locations where the 2 meet, which is right around downtown Charleston, that around there you can have flooding that is bigger than if you would have only the storm surge coming from the coast or only the river discharge peak coming from upstream, where those 2 meet. This process that the flooding due to multiple driver is larger than just from a single driver is what we call compound flooding. So here I mentioned storm surge and river discharge. You can also see it a bit broader, that you have like local wind setup, you can have waves coming from the coast, potentially urban drainage can have an influence, local rainfall, infiltration. So in general, say if any of these drivers or multiple of them happen at the same time, the flooding can be larger than if you would look at one of those processes individually. And this is especially true, for instance, for tropical cyclones, because so much happens at the same time. And therefore, it's important if you want to model these that you don't look only at the storm surge or only at the river input, but really investigate it as a joint approach. So just as an example, this is a study from some of my colleagues at the university that they were looking in the last 30 odd years, like how many co-occurring events there were that both discharge and storm surge happened at the same time. Well, there are differences globally in regions where that happens more often or less often. We especially see on the West Coast and the East Coast of the US. In general, you could say a lot more regions often impacted by tropical cyclones, that you can have really its potential for compound flooding, where we should model these by looking at all these different processes. And I don't know how that is in your group, but traditionally, if I look back to when I started here 5-6 years ago, often these processes were still looked at separately. So then, the river department looks mostly at the riverine flooding. The coastal department mostly looks at the storm surge. But in the region where those 2 come together, for a long time we were not including both these processes yet. So you could say in general there are like different domains. So there is more like a modeling domain, an oceanic domain, which is more a bit the larger scale. Tides and storm, tides and currents, storm surge, deep water waves. Then if you look purely at the coastal zone, you have like the nearshore waves that can start to shoal and run up and overtopping, and where the storm surge can lead to coastal flooding, and more the inland domain where the river discharge can inland in itself can already create flooding. It can also be that if there's a little bit of storm surge but a lot of river discharge coming down, it's still in your estuarine region, a lot of flooding could occur. So what we generally aim nowadays is for what I would call then coastal compound flooding, that we try to look at all these processes at the same time and within one numerical modeling exercise. But to illustrate a bit more why we should also consider waves in this, because often people, for good reasons, also with computational constraints, then we often look now maybe like, okay, we do look at tides and storm surge and combination with river discharge, but not yet about, so we don't always include waves in there. So I'm showing here an example in the Philippines. This is Typhoon Haiyan, 2013. This is a simulation of the storm surge. Maybe some of you have ever heard about a location called Tacloban, which is really a funnel where the storm surge was several meters and was pushed up really high. So this is the classic case. Okay, if you look at the storm surge and use that for coastal flooding, well, that's a good exercise. But what we are looking now is a location that is called Hernani, which is at the open coast. The continental shelf is very narrow here, so there's a low buildup of storm surge. It's less than 1 meter, and there's not this funnel that you see at Tacloban. In total, the maximum water level of tide and surge combined is less than 1 meter. But what happens there, this is footage of a village that's located behind a coral reef that's normally nice and protected from the waves. But while the storm surge was less than 1 meter, still this happens. So we can clearly see there are like these giant infragravity waves that are generated that wash away entire houses. And while the early warning systems at the time were only predicting storm surge, there was no warning given because it's less than 1 meter, nothing unusual. But there were these incredible infragravity waves generated over the coral reef, and just only due to this wave component, these entire houses were swept away. So we can actually model these with like a model like XBeach, but nowadays also with Sphinx. So what we can do, so this is what that location looked like. So the yellow line is sort of the edge of what the coral reef is. So normally, if you have just small waves, those waves break here, and basically at the coastline, just in front of your village, you hardly see any waves energy left. And then that imposes no threat to the community. But because this Typhoon Haiyan is like a Category 5 hurricane, and so offshore wave heights of like 15, 16 meters were generated, massive waves. And because there's not a lot of continental shelf or nothing, it's a coral reef, so there's basically no wave breaking up until you hit that reef. And these 15-meter high significant wave height of the short waves, those generate infragravity waves that become over 2-3 meters high. So if I start the simulation, this is an indication along this cross section, where you have an indication of the house where we saw the video that was around somewhere around here. You can see, well, initially the water level a bit lower, but then these large infragravity waves start to being developed, start to overwash over the beach, and then in the end go completely over that first ridge and then completely inundate the entire, basically the entire area until you hit the mountains. So the good news is we can actually model this type of phenomena, but we're not doing that all the time. And there's a good reason for this. So as I said, like in certain cases, waves can be very important. In many cases, for instance, if you look at like the location of Tacloban, where there's a lot of storm surge, it's less important. And therefore, often in national, state to national to continental scales, waves are often not included or in a very simple way. So what is sometimes done in global studies is that you calculate what the offshore wave height is, and then you assume, well, the wave setup is probably 20% of the offshore wave. Well, that is, of course, it is a estimate. Well, that's a good start, but it's still very simplistically. And the reason that is often done is that numerical models that can model these types of wave-driven processes, they are often very computationally expensive. So, for instance, you have models like Swash or XBeach or Business type models like FunWave. They can model these wave processes that happen over this reef, as in the simulation I just showed. But then often they take hours and hours and hours to simulate, just for simulating 1 hour simulation. So if you want to do that along a 100 or 1,000 kilometer coastline, let alone want to do that in an operational early warning system, that is just no matter how much computing power we have, it's just not feasible. So I would say in general, if you have ways, or there's sort of, if you want to model those, there's sort of a balance between accuracy and computational time. So you can have, well, the easiest method is ignore waves, and then simple ways that you either assume, for instance, that 20% of offshore wave height, or you can do a Stockton type of equation. It's a very fast, but lacks a lot of physics. On the other hand, you have process-based models like SWAN or X-speech fun wave that are very accurate. You take a lot of time, let alone if you go to something like OpenFOAM, CFD, then it's even more accurate, but then the computational moment completely goes off the scale. And what we want to do is try to be somewhere in this middle ground that we call like reduced complexity modeling, so that we still can give an accurate result, that we say, okay, the physics, most of the physics are resolved, and we have trust in the outcome, and then we can show compared to these process-based models that we're giving a pretty accurate result, but that the computation and time is significantly reduced. So this is an example in the last slide, that the same simulation for X-speech took like 3 hours or something to do, and the simulation that Martin ran with Sphinx for 1 hour only took like 10 seconds. So that's a completely different scale. And if you tune the model well and look at the results carefully, include the right processes, you can get an accurate result. So then I want to say something about the importance of probabilistic estimates. So far I've told you, like, okay, we want to consider all these types of different processes related to compound flooding. And then because we want to include more different processes, then the modeling becomes more complicated, especially if you want to do it quickly. I didn't mention it specifically, but in general, I think everyone wants to model larger and larger scales. So not only look at the study of your 5-kilometer coastline, but do it the entire state of Texas, or do the entire US coastline. So therefore, you want to be able to model larger scales. And what is also important is to include probabilistic estimates. So as you all know, especially for hurricanes, there's a lot of uncertainty in what the potential track will be. If you're doing forecasts, this is an example of Hurricane Ian last year. So it is somewhere in the Caribbean, and these are just estimates of all different types of models that we're trying to predict what the exact track Hurricane Ian will become. And this is already a scale of hundreds of kilometers. So that indicates there's a big uncertainty. Well, will the hurricane go like this, or will it go like this? And then if you try to model what is the impact on your coastline, that of course matters everything, whether it will make landfall here or here. If you look at the location somewhere, but try to predict what the impact on the coastline will be there. The probabilistic estimate can be important for all types of storms, but especially when dealing with hurricanes, this is very important. This is not only in the forecast mode, as I showed in the previous slide, but also in general, if you want to do a climate variability assessment, have an idea, okay, I want to build this structure somewhere along the coast, what is now like a proper representation of my hurricane climate, then it's important to look at hurricanes closely, and not only look into the last 50 years of data, because then maybe there's a big hurricane that makes landfall every 5 years or every 10 years, and then it's very hard to do proper probabilistics just based on relatively limited set of events. And because we want to assess this probabilistics for a large scale of coastline, this means that we need fast computations. And I will show some examples for Hurricane Ian to illustrate a bit more why this looking at it in a probabilistic way is important. And also give you one example for more like climate variability study or tool DC-wise. So this is a simulation of Hurricane Ian. So my colleagues were running as part of a NOP project for the Office of Naval Research. So there, while the hurricane was happening, while they get a new forecast of the hurricane track and the wind speeds every 12 hours, I believe. They had an online platform, and they, just as some other modeling teams, they were running these predictions of the hurricane track. They were running it in a bunch of different models, and then they, for instance, could make simulations with the Sphinx model. Here's an example of the water levels at Fort Myers, basically exactly where the hurricane made landfall. And you see then initially that there's a lot of rainfall already. It starts to fill up the initial estuaries, and then the hurricane went over Fort Myers and created this big storm surge. So we can model these types of events, trying to run the best track. As I already illustrated before, there's a lot of uncertainty in how the cyclone track will be. So we then can start to look at is something like ensemble forecasts. So there are different methods. For instance, the method of Maria, that when you have an estimate at different times in interval before landfall, that based on the best track, you can make like a realization of alternative synthetic tracks that are potential candidates what might happen as well. So with this method, they are all ranged around the original track, and then there are rules for, okay, well, you can have a certain cross-track error, you can have a certain long-track error in terms of the propagation speed, and then you can create ensembles of 100 to 1,000 different realizations. And you can see with longer lead times up to landfall, the range of where the cyclone may go becomes is still very large. If you then go closer to landfall, they become more and more confined. And when having these different types of checks, that also means that you can, if your modeling system is fast enough, you can run all of these before you get the new update of the best track 12 hours later. And thereby, if you run all of them, you can sort of give a sort of probabilistic estimate of what you think the risk is for a certain location that the hurricane might lead to significant damages there. So this is an illustration of how big the range of most of the tracks going through a certain location is, depending on the lead time. And this is what I always find quite an interesting plot. So this is the same water level at Fort Myers that we saw in the previous simulation. So we look at this water level, and then we look at it once it's simulated with all these different tracks, all these different realizations. So the blue line in this case, so this is time on the x-axis, water level on the y-axis. So there's a little bit of tide, there's a bit of set down, and then you have the big storm surge peak. So this is what is modeled by the best track. And then the gray line is of all the 100 different ensemble members. So there's some hurricanes where it makes landfall a bit more north, a bit more south, some that make a bit earlier, landfall a bit earlier, that they move a bit, propagate a bit faster, some a bit slower. And you can see there's this large range of what might happen. And from these ensemble members, you can, for instance, calculate also what the confidence interval is. So this is, well, then this red spread around the best track, but it shows that basically that anything might happen between a water level between -2 meters and +4 meters above mean sea level. So this is, of course, a huge uncertainty range that has to do with what exact track that the hurricane will take. So in this case, taking the best track, that was already quite a good estimate, but it can also be in regions where especially the tide is larger. So if you go more to the location, for instance, Bangladesh in the Bay of Bengal, where the tidal range can be up to 3-4 meters, total tidal range of maybe almost 6 meters. So there, in that case, it matters a lot if you get the timing with the peak of the tide exactly right or not, and just make a difference if the storm surge becomes, the total water level becomes 6 meters or just 3 meters. So then this timing and this uncertainty becomes even larger, and then it becomes even more important to include a lot of ensemble members and look at this forecasting in a probabilistic way. So this is an example of a probabilistic flood map or maximum water level map that you can make from this. So now we're not looking just at the water level at Fort Myers in time for all the different realizations, but we're looking in space, so that you can calculate for every single grid cell of all of your swings, your flood simulations per track, per cell. You can then calculate what your for a certain exceedance probability, what you think is the certain storm level. And then you can say, well, there's a certain water level that's probably being exceeded. And then you can get estimates of like, well, in this certain region, especially where there's a funnel, there's probably the largest chance of a high storm surge. And one of the open questions I think still is also, well, now we're showing that we are able to simulate this quickly and probabilistically in an early warning system. But then also the question becomes like, okay, how are you going to communicate this afterwards with more like policymakers that maybe don't fully grasp the concept? Okay, we've run a lot of simulations and different types of track, and we calculate certain event with certain exceedance probability, what might happen, and they then have to interpret that. Okay, does this mean do I have to evacuate my people or not? So I think that is a little bit still an open question, but that is becoming relevant now. Okay, if you can make these probabilistic estimates, like how are you then afterwards going to translate this to actions for more policymaker type of managers? But this is so this was an example so far for more like an operational probabilistic early warning type of setting. And you can also, oh yeah, one more slide on this. So this is from this NOP project. So what we're doing in an operational way is that they get like the COEM's meteorological forcing, the best track, and there are large scale searching wave models, combination of Delta-3D, swings and hurry wave. Then there are all swings models along the coastline that calculate the flooding, but then they also, for certain hotspots, they will calculate also with X-Beach, actual barrier island reaching. Right. So last year during Hurricane Ian, this was still deterministically. Now they're going to make this probabilistically, include these example members in this fixed project. And as I was going to say, so you can also look at it in a more thermal climate variability studies. So that's more like if you want to get an idea, okay, what is the extreme water level in front of the Texas coastline? What you often do nowadays is that you start to look into synthetic tropical cyclone tracks. You can do this in many ways. There are like these GPM type methods that the Army Corps runs. And there are different types of synthetic tropical cyclone track generators, like Storm or the ones from Kerry Emmanuel. And we have also at Dotars, we have an open source version of this as well. It's called TCWise, Tropical Cyclone Wind Statistical Estimation Tool, if I'm remembering the abbreviation correctly. But the idea is that you, based on the climate of the original tropical cyclone tracks, the historical ones. You can create more realizations, so 10,000 of years of climate based on the statistics of the original climate. The idea is that you then get a lot more realizations of the same climate. So basically every single combination of, well, I have this location at the coastline, it might make landfall 5 kilometers more north or south, or with moving a bit faster, or a bit more intensity. Like all these different combinations are then included, and those you can also run in numerical models, 3D or things or EDSER. And then this takes, of course, also computing powers, and then it's also nice to have a faster model. So the tool is just a MATLAB script-based tool that you can all download and adapt or build onto in case you want to show one example of why this matters. It's maybe a little bit of a detailed plot, but it's from a paper that we did that we published last year. So we were looking in the Bay of Bengal in front of Bangladesh of what were the extreme storm surge possible. And we ran that both for only the original climate. So then there was a hurricane that maybe it made landfall once every 5 years or something. So that is the black line. So we ran, for instance, all these tracks. We ran it in a Delft-3D flexible mesh and swarm model. You calculate the maximum storm surge for every single cyclone. You can make an extreme value analysis curve, and it looked something like the black line. And you can do the same based on the synthetic climate. In that case, we ran 1,000 years of tropical cyclone tracks. We ran all of those in the Delft-3D model as well. If you then start comparing the two, then you see that the estimate based on the synthetic climate is a lot higher, almost a meter in some cases, which just shows that if you just look at the historic set of events, then not all possible combinations that might impact your coast, not all of those have happened yet in the past 50 years of recorded climate. And therefore, it can be a good thing to look with a probabilistic tool, look what actually might also happen, and with a lot more realizations if it makes landfall a bit to the north or the south, with all these combinations in there. And in case of Bangladesh, especially where the tidal range is a lot larger than the combination of the landfall, the hurricane making landfall during the spring cycle or the neap tidal cycle, the exact timing with high tide, low tide makes all the difference. So then it's very important what you include in your models. All right, I'll take a quick sip of water. So what I've shown you so far is sort of leading up to the story is that, okay, we want to consider compound flooding. So we want to, for looking at coastal flooding, not only evaluate the tide and the surge, but we should also look at rainfall, we should look at river discharge, and that waves should be considered too. In general, we want to model larger and larger scales along the coastline, and it's important to look at probabilistic estimates, especially in hurricane-affected areas. But putting all this together means that you want to run a lot more processes, much larger scales, much more realizations, and with traditional software, advanced numerical models like EDSER or Delft-3D or Mike, this is often just not feasible. Sometimes you can get away with that partly if you can run on a supercomputer with 1,000 cores, but at some point you're going to start hitting limits. And this was for us then about ours. The starting point on looking, okay, we need faster numerical tools to look into this compound flooding and have a more probabilistic estimate evaluating larger scales. And this is both true for wave models, but this is more like your offshore model, like Swan, or WaveWatch, or WAM, or as more these compound flood models looking at the flooding specifically. And I will focus hereby on two new wave models, hurry wave and snap wave, and then more detail to the Sphinx model, which some of you are already familiar with. So the hurry wave model is developed by my colleague Martin Normand. It's also a third generation spectral wave model, similar to Swan. I hope Jay already explained more about this last week. So you're already familiar with that. And then what Martin did is basically take the same type of equations, same type of physics, putting in a little bit simpler numerical scheme, code it in a bit smarter way, and what you end up with in the end is a model that's about 2 orders of maximum magnitude faster than Swan in calculating non-stationary waves. This is an example of a model in Hawaii. And then once I will run the simulation, it will be the same hurricane track that goes in hurry wave as in Swan, and you will see that the simulations the results look very similar into the propagation of the wave heights. But then the nice thing is that while Swan, while running on this PC with 2400 seconds, on his CPU, on his normal computer, it only took a minute, and then especially when running on the GPU, it only was a matter of seconds. So this is a very big change in computational demand, which is awesome. And it also makes the possibility, since we can be run so much faster, that it's also a lot easier to say like, oh, now I want to run 1,000 different realizations to get my probabilistic hurricane estimate correctly, or you can start modeling larger scales and all of that. So by making these faster models, it also allows us to do many of those things. So this is more for the like a non-stationary type of model for large-scale propagation of, for instance, waves due to a hurricane. More for near shore, we also saw that a model like Swan is a bit too slow for the purposes we want. So if you think of a coupled fill through the flow wave type model, you're using it to calculate the wave in the setup, but a lot of the time that goes into a lot of physics and a lot of things in Swan is maybe not everything you actually need for that. So my colleague Daniel Wolfink, he started developing this snap wave model, what they call it. So this is more for modeling close to the coast, more near shore. And this is a stationary model, like Swan, and it uses solves the wave action equation with time-dependent forcing, which for instance also expeeds surf beat. It's a bit similar to the Hiswell model. They coded it now in sort of in a fast, smart way, going through unstructured grids. And what you can do with that is now in a very quick way. So this is the entire coastline of Bangladesh. You can calculate the wave heights on that using unstructured grid very quickly. And what we are now also adding is that we can do what I'm doing in my PhD research is that you can actually also with this now calculate what the infogravity wave height is everywhere in the domain, which means that you don't need to make XGBoost models for the entire coastline. Well, if I then now go to the Sphinx model, so we've seen we want these faster computations. So what we started is this new open source Sphinx model, which stands for super fast inundation of coast. And here we also have something like this balance between accuracy and computational demand. So a very simple model, something like a bathtub model, process-based model, something like L3D or ETSR. We want to be in this region where it's a lot faster and you don't lose a lot of accuracy. It's based on the equations of Paul Bates. 2010, which is also the refereeing model list flood. And then we have added all these processes that are relevant for compound flooding, as regard the river discharge, the storm surge, and the waves. And the idea is that it is like this fast, quick scan model. And if you then want to look in more detail, certain very specific processes, or 3D layers, or 1D, 2D coupling, or sediment transport, or temperature, salinity, then you can go towards Delft3D. So just to show that this model can actually do very nice things. So this is an example of what we published in a paper originally. This is a case in Jacksonville, Hurricane Irma. So this is a location along the St. Johns River. We're already quite far, 40 kilometers upstream already from the coast. Looking at this location to the maximum water levels, and we compare it to the old Delft3D4. And while that took, for 6-day simulation to run on IPC, that took 40 hours to do the simulation. So 15 minutes, while getting the peak storm surge exactly the same. So that was already great. And when we later started to do more innovations, we added this subgrid type of functionality that we can incorporate the bed levels, or especially if you have high resolution data that is finer than what you use in your grid resolution of your model, then we can actually include these in a nice way. And we then can show that you can, even on the 200-meter grid resolution, which is relatively coarse for such a narrow river around here, we can still get the propagation of the tidal signal correctly all the way 80 to 90 kilometers inland using this subgrid type of approach. Now, what we can now do is that we can also, because the model is so fast, we can start modeling larger scales. So we've done a project in the southeast coast of the US, where we run about 80,000 simulations using 5 different model domains of swings, so that we can really incorporate all these probabilistics of different tropical cyclone tracks, different northeastern type of storms, and look at probabilistic flood maps. What we've also done in Australia for about 7,000 kilometers of coastline, make a lot of connecting swings models, and those are now running operationally in the system predicting compound flooding. I've had 2 slides showing that we can actually simulate flooding then very nicely, even while having this very large scale setup. So these are 2, this is the observed flooding, and in blue is the simulated one. And then we can show for some time series that we can nicely model these. Well, in terms of time, I will move forward a little bit. So in case you would dive into wanting to make a swing model yourself, you can find online that the easiest way to do that now is using a Python package called HydroNP. And with this, it's easy to make models in a reproducible way, but also, for instance, make coupled river flooding and coast models. And then you can make different types of models based on the same data. So it's easy to connect these. This is also all available open source. And one thing that is nice, I think, to show you what we have been doing recently in terms of new developments in the Sphinx model. So far, we have already been doing for the last years a lot of nice work with component flooding, with all different types of processes. But now we want to include waves also in a better way. And this utilizes new developments that we're doing, called something like quadtree mesh, so that we can do local resolutions, local higher resolution, and new wave types of forcing. I will show a little bit on that for Hurricane Michael, that Martin modeled in Florida. So this is a location called Mexico Beach, where a lot of houses were directly impacted by the hurricane. What Martin did when he made the Sphinx model, traditionally we have everywhere the same grid resolution, but using this prototype quadtree mesh, you can make local refinements. And this is especially important if you want to model waves dynamically, then you need, well, something like a 20-25 meter grid resolution or finer. Otherwise, you can just physically, numerically not resolve a wave, but you don't want to have that everywhere in your domain. Some parts you want to, especially offshore, you want to make it coarser. But with this quadtree, you can refine this in a nice way. And the quadtree just means that every cell, if you do a refinement, is just a factor of 2 finer. So it's a sort of a structured way of unstructured mesh. And what Martin now added is that close to the coast, you can put in these wave makers, as we call them. So this is a boundary condition, and that is also an X-speech. But what in X-speech you can only force is along one of your offshore boundaries. What you can do now with these wave makers, you can put them anywhere you want, close to the coast, generally somewhere in the surf zone, and then from there you can start forcing dynamic waves close to the coast. And by this, you save a lot of computational time, and also means that you don't have to run, for instance, an X-speech type of model. And what you can now do with this is make a simulation that can very quickly assess wave-driven flooding during a hurricane. So in this part is the deeper type of the model, and around here is where we start to force the waves. They start to propagate inland, where you have to find resolution. And further inland, it's not so much the direct impact of the waves that you have to resolve. There it becomes more like the general storm surge that comes rushing in. So here we have coastal resolution again. So the nice thing is with this quadtree type of meshes that we can actually do this now. And to show you that these waves matter, here on the left, there's a comparison with high water marks observed versus modeled here with waves, and here on the right hand side without waves. And you see, especially in this zone close to the coast, where you have these houses that are washed away, they're in order to meet these peak high water marks, you need to have these wave-driven processes included. And now with these prototype versions, that is actually possible. Then the last thing I will quickly talk about is working open source and open access, and then I will go to the end so that I can leave some room for questions. So the nice thing we want to do in general at Deltares is our philosophy is dare to share. So all these models that I mentioned so far are open source, so you can all just download them and use them. And we think it's very nice also to connect with academia, that everyone can just use these models. And because they're open source, it's also easier for people to add certain models to it or understand what's happening in the code. And now, for instance, with Sphinx, we already got some pull requests and ideas or issues that other people just put into our GitHub page. They can suggest a change in the code or an example in the documentation, request a new feature, which I think is very nice. So they can collaboratively start developing these models. And these are some example locations all around the world where Sphinx has already been applied so far. And I think with that, I will skip a few slides. So these were some simulations in developing countries, where it's also very relevant to have fast simulations. And last, very briefly, I want to briefly mention. So far, myself in my work, I mostly focus on calculating flood maps, but there are also tools like hazards that go to more calculating the amount of people affected and certain risk. So we also have a variation of that called Delphiat that you can also build using HydroMT. You can directly link your Sphinx flood map to. So if you're interested, you could check that out. And another nice thing is that we're developing something called Flood Adapt. That incorporates both Sphinx and Delphiat, but that's more meant as a is a tool for non-expert users that they can actually look at the location of Charleston and start playing like, okay, hey, my current flood risk is this, and maybe these houses are affected. And then by changing, adding a seawall or something, then your flood risk would reduce. I'm going to my final slide. I've been talking for a while now. So what I hope that you got some inspiration that we are developing these new fast tools for making probabilistic large-scale assessments, forecasting high costs, and combined flood modeling possible. For this, we developed the new fast models, HurryWave, SnapWave, and Sphinx, which are all available open source, or we are willing to share them. Not yet. There are also important aspects for calculating build damage, load disruption, and adaptation measures that are also becoming available now based on these software models are also available openly. And this gives a lot of new opportunities for applications, for instance, also in developing countries that have less computational resources. So with that, I know it's a lot of information, but I hope it was interesting and give you some inspiration, some ideas of what we are developing. And yeah, happy to answer any questions in the time that's left.
Okay, thank you very much, Tim. Very informative. Any question for Tim? In chat, no. I have. Yeah, go ahead, Bridget.
Tim, I have one question. I mean, are you looking at atmospheric rivers at all in flooding? I don't know if Brisbane flooding was linked to atmospheric rivers or not. And you can see those coming along in California. You can see them 6 or 7 days out. So have you guys been looking at those at all for flooding?
Atmospheric rivers, not specifically in detail, but in principle, we can include all processes. I would think like wind and pressure and rainfall. I think it would be possible.
And I guess the reservoir management would be another aspect. You know, I guess maybe difficult to figure out how they're going to manage the reservoirs.
Yes, that's true. So what we now did in Australia is that we have a hydrological model. It's called WFlow, but they can actually include some more detailed information on how you can use how a basin or a dam might be managed. So they include the hydrological model, includes the entire upstream catchment, some of these rules, and then we start the Sphinx model a bit more downstream from there. So then we get from this hydrological model, we get in the input what is the river discharge, and that is put then automatically into the Sphinx model and like an operational system. So then we go about it in that way.
Thank you so much. Excellent presentation, and really pleased that you guys make everything open source. That's fantastic. Thank you.
Alex?
Yeah, so I have a question. So in the US, I guess NOAA is developing this UFS, like a unified forecasting system. I guess you're probably aware of that. So I'm just wondering, like the interoperability, between Sphinx and other like a NOAA model or NOAA forecast. For example, in the ensemble-based hurricane compound flooding use case, I guess you show that you developed this 96 hour all the way and then day ahead forecast. So I wonder, I mean, did you incorporate the land-based hydrology like a river flow in those kind of forecasting models? And your vision for making the models more compatible with some existing NOAA components?
Good question. So right now in that operational project, we're not using river input from the national water model. But in the project that I showed, that was the southeast coast of the United States, so it was not an operational system, but a hindcast. So there we included basically the storm conditions of the last 40 years. There we coupled upstream with the national water model. So as long as you have some scripting, it doesn't really matter for Sphinx itself, like where a river discharge input comes from, whether it is from a national water model or from a different source. That is in itself possible if you have just the right platform that runs the models operationally. The same is like if there's a storm surge modeled by a different model that is not Sphinx or Del3D. If you have just a small, for instance, Python converter that writes it to the input of Sphinx, that is in itself all possible. I think there are already some tools or some platforms out there that can do that, like Delfuse, but also some other ones. So that's very interesting to include those if possible.
Oh, okay, thank you.
Okay, time is almost done, but take one more question, Justin.
Yeah, my question is a pretty simple one. I was just wondering, you showed two global maps in your presentation. Early on, you showed a map, if I understood it correctly, of the prevalence of sort of compound flood events. And then you showed sort of toward the end of your presentation, a global map showing where some of these tools have been applied. I was just wondering if you are sort of looking at the comparison between those two and kind of targeting where further studies would be or most impactful, most useful. I was just wondering about that.
Good question. I haven't looked at it that way, that we build the model specifically for where those problems are most occurring. But I think, well, in a way, like where we got the most requests for projects to build these models are mostly in those type of regions. So there's of course a correlation in that sense that the most locations where you have these problems and these multiple flood drivers and this where you have these questions arising, that there you want to have is the most nice use to use these faster type of models, and then we get the questions also from there. I think some of my colleagues more at the university, they look generally a bit more at the global scale, so they're thinking of also like, how can we just make Sphinx models for a lot of these areas and then start calculating them in that way, like the compound flooding potential. But it's still underway. But it's a good question.
Yeah, I mean, I was just thinking about it. I mean, sometimes the need translates to a voice, but not always, right? And so what really drew my attention, for example, was the northwest coast of Africa, right? That was a really hot spot in terms of occurrences. And, I could see where for a number of reasons that you might not necessarily get a lot of voices, asking or funding work in that area. But obviously from that other data, it's needed there. So that was just kind of where my thought came from. Overall, great presentation. It was interesting. Thank you.
Thank you, team. It's almost done. So your talk and your presentation give me a lot of homework. So thank you so much for your time and talk today.
You're welcome. Yeah, if anyone has any question about any of these models, you can just email me or one of my colleagues. All the stuff about Sphinx is open source online. The SnapWave and HurryWave models have less documentation so far, but if you ask us personally, we can get you in touch with the right person. I think should be able to share those.
Keep in touch.
But thanks a lot for allowing me to give the presentation, and happy to collaborate with any of you along the way if it would work out.
Okay, thank you very much. Have a good day. Bye bye.
Thank you. Have a good day. Thank you.